The universe is held together by an invisible hand. Everything you can see, from the stars above to the ground beneath your feet, accounts for less than 5% of reality. The rest is a profound mystery, and the largest piece is called dark matter. This unseen substance makes up roughly 27% of the cosmos, acting as a cosmic glue that sculpts galaxies and keeps them from flying apart. By the end of this journey, you will understand the compelling evidence that proves dark matter is real and why it is the universe's essential scaffold. We will uncover why galaxies spin too fast, how light bends around nothing, and what strange particles might lurk in the darkness. What does it mean that most of reality is completely hidden from our senses? Her discovery would not be ignored. Astronomer Vera Rubin spent countless nights at the telescope, meticulously mapping the motion of stars within the Andromeda galaxy. She expected a familiar cosmic rhythm. In our own solar system, planets closer to the Sun whip around at incredible speeds, while distant worlds like Neptune move in a slow, stately orbit, their pace dictated by the Sun's weakening gravitational grip. Rubin anticipated the same pattern in a galaxy, with stars near the brilliant center orbiting furiously, and those at the faint outer edges drifting along slowly, almost lazily. The data told a different story entirely. Stars far out in the galactic suburbs were racing along just as fast as those downtown. The rotation curve, the graph plotting speed against distance, was not a steep drop but a stubborn, unsettling flat line. This simple observation shattered a basic expectation. According to the laws of gravity as we understood them, a galaxy made only of the stars and gas we can see should fly apart. Those outer stars were moving with such velocity that the gravity from all the visible light in the galaxy could not possibly hold them in orbit. They should have been flung into the intergalactic void long ago. The only logical explanation was the presence of something else, a vast amount of mass we could not see. Think of a playground merry-go-round. If all the children sit in the center, it spins easily. But if you place several children on the outer edge, the ride becomes much harder to spin and requires a stronger push. Now, imagine that merry-go-round spins with a perfectly even, smooth speed, but you can only see the children sitting in the middle. You would have to conclude there are unseen children clinging to the outer rings, their hidden weight dictating the motion. Vera Rubin's work provided the first robust, undeniable evidence for this cosmic hidden weight. She famously stated, "What you see in a spiral galaxy is not what you get." Her perseverance revealed that every spiral galaxy is embedded within a gigantic, diffuse sphere of invisible matter, a halo extending far beyond the last visible star, its gravity the only thing keeping the stellar disk intact. This was the first major crack in the universe's visible facade, forcing science to confront a profound question. If what we see is not what holds galaxies together, what does? Rubin's discovery gave us a profound clue from the inside of galaxies, but the next piece of evidence came from looking right through them. Einstein's theory of relativity gave us a prediction. He said that mass warps the very fabric of space and time, like a heavy bowling ball placed on a stretched rubber sheet. Anything moving through that warped space, including a beam of light, will follow a curved path. This means a massive object, like a galaxy cluster, can act as a cosmic lens, bending and magnifying the light from objects far behind it. Astronomers call this gravitational lensing, and it is one of the most direct ways to see the invisible. Imagine looking through the bottom of a wine glass at a distant streetlight. The glass distorts the light, stretching it into a strange, smeared arc. A galaxy cluster does the same thing to the light of galaxies billions of light years behind it. We see multiple, stretched, and distorted images of those background galaxies, a celestial funhouse mirror created by gravity alone. But here is the mystery. When scientists measure how much the light is bending, they calculate how much mass must be in the foreground cluster to cause that distortion. Time and again, the number is staggering. The visible galaxies and hot gas in the cluster account for only a fraction of the gravity required. The rest, the overwhelming majority of the mass bending that light, is completely dark. This is not an inference about motion inside a galaxy. This is a direct measurement of gravity's fingerprint, and it points to a vast ocean of dark matter enveloping every cluster. Projects like the Hubble Space Telescope have used this technique to create detailed maps of the invisible. By studying the intricate patterns of distorted light, scientists can literally trace out where the dark matter is, saying they are mapping the unseen scaffolding of the universe. Perhaps the most striking proof comes from cosmic collisions. Take two massive galaxy clusters smashing into each other at millions of miles per hour, an event like the Bullet Cluster. In such a titanic impact, the clouds of hot gas, the normal matter that glows in X-rays, slam together and slow down like two clouds of smoke colliding. But the dark matter, which does not interact with itself or light, simply passes right through. Using gravitational lensing, astronomers could map where most of the mass ended up after the collision. The result was astonishing. The bulk of the mass, the dark matter, was in two clouds that had sailed clean through the collision, now separated from the visible gas. It was as if two ghosts walked through a wall, leaving their visible shadows behind. This observation proved dark matter is not just an idea. It is a tangible substance that behaves differently from anything made of atoms. It does not glow, it does not crash into itself, but its gravity is undeniable, sculpting the paths of light across the cosmos. So we have two powerful clues, one from the spin of galaxies and one from the bending of light, both telling the same story. Most of the universe's matter is hiding in plain sight, but this raises an even deeper question. If it is real and it is everywhere, what in the world is it actually made of? The silent fingerprints of dark matter are not just in the present cosmos, but etched into its very first light. To find them, we must journey back to a time before stars, before galaxies, before even atoms as we know them. Roughly 380,000 years after the Big Bang, the universe underwent a profound transformation. It had expanded and cooled from a searing plasma of particles and light into a state cool enough for electrons to finally combine with protons, forming the first neutral hydrogen atoms. In that moment, the fog cleared. Light, which had been constantly scattered and trapped, was suddenly set free. That first flash of liberated light has been traveling across an ever-expanding universe for over 13 billion years. Stretched and cooled into a faint microwave whisper that permeates all of space. We call it the cosmic microwave background, and it is the oldest picture we will ever have of our universe. Satellites like Planck have mapped this ancient glow with exquisite precision, revealing it is not perfectly uniform. It is a tapestry of incredibly subtle temperature variations, tiny ripples of slightly hotter and cooler patches. These ripples are the cosmic seeds of everything. They represent the slight over-densities and under-densities in the early universe, the places where matter was just a little more crowded, and here is where dark matter writes its signature. Ordinary matter, the protons and electrons that make up atoms, was under immense pressure from that intense early radiation. The pressure created waves, like sound waves pushing against any attempt to clump together. Gravity from normal matter alone could not overcome this pressure quickly enough to build the vast structures we see today. Dark matter provided the crucial anchor. Because it does not interact with light, it was immune to that radiation pressure. From the very first moments, dark matter could begin to clump together under its own gravity, forming invisible wells of potential. Those gravitational wells then acted as traps, gently pulling the ordinary matter, the future stars and galaxies into them once the universe cooled enough. The patterns in the cosmic microwave background are a frozen record of this partnership. By measuring the exact size and distribution of those temperature ripples, scientists can perform a cosmic accounting. The data tells an unequivocal story. To create the precise pattern we see, and to explain how galaxies formed in the time we observe, the universe must be made of about 85% matter that is dark and only 15% ordinary atomic matter. This evidence from the universe's infancy is perhaps the most compelling of all. It is not just about how galaxies spin now or how light bends today. It is a direct message from the dawn of time, confirming that dark matter was not an afterthought. It was a foundational ingredient woven into the fabric of the cosmos from its first moments, its silent gravity providing the blueprint for everything that followed. With its existence so firmly established by the universe's own baby picture, the mystery only deepens. We know it is there. We know it shaped everything. So what, in all of creation, could it possibly be? We have mapped its gravity across the cosmos, from the spin of galaxies to the bending of light and the whispers of the first universe. Yet its true nature remains a silhouette. To find it, we must first understand what it is not. This process of elimination is not just scientific housekeeping. It is a vital narrowing of the path through a dense forest of possibilities. Let us start with the most intuitive guess. Could dark matter simply be ordinary things we know, just hidden, vast clouds of cold gas or immense swarms of dim, planet-sized rocks drifting between stars? Astronomers call these massive compact halo objects. While these certainly exist, detailed surveys have ruled them out as the primary answer. Such objects made of normal atoms would interact with light. They would block or bend the light of stars behind them in specific, detectable ways. We have looked for these subtle signatures for decades, and the numbers simply do not add up. These hidden ordinary objects might account for a tiny fraction of the darkness, but not the overwhelming 27% of the universe. Another dramatic candidate is black holes, especially primordial ones theorized to have formed in the chaos of the early cosmos. Yet again, observations constrain this idea. If dark matter were primarily black holes, we would see their gravitational effects everywhere, from distorting starlight to influencing the orbits of stars within our own galaxy in ways we do not observe. The collective evidence tells us dark matter is not made of familiar stuff hiding in the shadows. It is something fundamentally different. Some have proposed that we do not need a new substance at all, but a new law. This idea, called modified Newtonian dynamics, suggests that gravity itself behaves differently on the vast scales of galaxies than it does in our solar system. While this is a creative and important avenue of inquiry, it struggles to explain the full suite of evidence. It can account for galaxy rotation, but it has a much harder time with the bullet cluster, where the gravity is clearly separated from the visible matter, or with the precise patterns in the cosmic microwave background that demand a specific type of unseen matter. The consensus, built from multiple independent lines of evidence, points away from a tweak to gravity and toward a new particle. So what about antimatter, the mysterious mirror of our own atomic world? When matter and antimatter meet, they annihilate in a flash of energy we could detect. If dark matter were antimatter, the universe would be filled with the glow of these constant collisions. The silence of our gamma-ray telescopes is deafening, telling us this is not the answer. By stripping away these possibilities, the portrait of dark matter comes into sharper, stranger focus. It must be a particle, but one utterly foreign to our experience. It does not absorb, reflect, or emit light. It passes through planets and people as if they were not even there. As one physicist put it, it is something that interacts with our world only through the gentlest of touches, gravity. This process of elimination is not a dead end. It is the essential guide that leads us to the most thrilling frontier of all, the direct hunt for a ghost. This narrowing of possibilities leads us to a profound and elegant idea. What if dark matter is a particle predicted not by what we see, but by the beautiful mathematics of what could be? The leading theoretical candidate is known as a WIMP, a weakly interacting massive particle. The name itself tells a story. These are hypothesized to be heavy, much heavier than a proton, and slow-moving, which fits the cosmic need for a substance that clumps together to form halos. Most crucially, they interact only through gravity and the weak nuclear force, the same force behind certain types of radioactive decay. This makes them fantastically shy. A WIMP could pass through a light year of solid lead without a single collision. For physicists, this is not just a convenient guess. WIMP emerge naturally from a grand extension of our current understanding called supersymmetry. This theory proposes that every known particle has a much heavier superpartner. The lightest of these superpartners would be stable, electrically neutral, and would have existed in vast numbers in the early universe, perfectly fitting the description of a dark matter particle. It is a compelling convergence where solving one of the biggest mysteries in cosmology might also complete the picture of fundamental physics. But a beautiful theory is not enough. We must find the particle. To do that, scientists have gone to extraordinary lengths, quite literally. They have built cathedrals of silence deep underground. In former gold mines, under mountains, and within vast caverns, experiments like LUX and xenon 1T wait in near-perfect stillness. Their core is a chamber filled with tons of ultra-pure liquid xenon, cooled to extreme temperatures. The concept is breathtakingly simple, yet its execution is a pinnacle of human engineering. The entire apparatus is a trap designed to catch a ghost. The hope is that once in a great while, a passing WIMP from the halo of our own galaxy will strike the nucleus of a xenon atom. That tiny, unimaginably rare bump would produce a flash of light and a trickle of electrical charge. Isolating that signal is the monumental challenge. Every known source of interference must be eliminated. The detectors are buried under thousands of feet of rock to shield them from cosmic rays. The materials used are meticulously selected for their low radioactivity. The scientists are, as one researcher described it, listening for a whisper in a hurricane. They must distinguish a potential dark matter interaction from the constant background chatter of natural radioactivity, from stray neutrons, from cosmic muons that penetrate even the deepest rock. So far, the whispers have not been heard. The detectors have grown larger and more sensitive with each generation, pushing the boundaries of what is possible, and in doing so, they have ruled out vast territories where WIMP could have been hiding. This absence of a signal is itself a form of discovery, forcing us to look deeper and think broader. It raises a thrilling possibility. What if the universe's secret ingredient is something even stranger than we imagined? The silence from the deep underground laboratories is not a sign of failure, but a call to broaden the search. If dark matter is not a WIMP, what other ghost could it be? The universe's hidden architecture might be built from something far lighter or something even more elusive. Two fascinating candidates have stepped into the spotlight, each with its own compelling story. First, consider the action. This hypothetical particle was born not from cosmology, but from a puzzle in the heart of the atom itself, a fine-tuning problem in the strong nuclear force. To solve it, physicists predicted an ultra-light particle, billions of times lighter than an electron. If actions exist in vast numbers, they could collectively make up the dark matter, but they would behave less like discrete particles and more like a pervasive, cosmic wave washing through everything. Their detection relies on a strange quantum quirk. In the presence of a tremendously powerful magnetic field, an action should very occasionally convert into a faint microwave photon. Experiments like the Axion dark matter experiment use supercooled resonant cavities, essentially high-tech radio receivers, tuned to listen for this specific whisper from the dark matter sea. Think of the difference between a WIMP and an action like the difference between searching for scattered pebbles and sensing a subtle shift in the tide. One requires catching a rare, heavy impact, the other demands sensing the collective hum of an ocean. Then there is the sterile neutrino. We know neutrinos exist, ghostly particles that barely interact with anything, streaming from the sun and through our bodies by the trillions every second. A sterile neutrino would be a heavier, even more aloof cousin. It would interact only through gravity, making it a perfect dark matter candidate. Its signature would be indirect but dramatic. If these particles are unstable, they could very slowly decay, and one of the products of that decay would be a detectable X-ray photon with a very specific energy. Astronomers are now scouring the X-ray sky with space telescopes, looking for an unexplained, faint emission line that cannot be attributed to any known gas or star, a spectral fingerprint of a dying dark matter particle. This diversity of ideas reveals the incredible creativity of the hunt. Scientists are not just building one kind of trap, they are engineering an entire arsenal, from ultra-quiet cavities listening for a wave to telescopes scanning for a telltale glow. They are preparing for every possibility because the universe has already shown it is far stranger than we expected. Each empty result from the WIMP searches makes these alternative pathways shine brighter. We are left with a thrilling, open-ended question. Is the cosmos held together by a sparse rain of heavy particles, a coherent wave of unimaginable lightness, or the slow decay of a secretive neutrino? The answer is out there, hidden in the data, waiting for its signal to rise above the noise. That cosmic blueprint written in the first light required a builder to bring it to life. In the beginning, the universe was almost perfectly smooth, a near-uniform sea of hot particles and radiation. Yet, imprinted within that smoothness were the faintest of ripples, quantum whispers left over from the Big Bang itself. These minuscule variations in density were the seeds of everything to come, but on their own they were powerless. The ordinary matter, the protons and electrons, was trapped in a furious dance with light. The radiation pressure was so intense it prevented this normal matter from collapsing under its own gravity. It was too hot, too energetic, too diffused to clump together into anything meaningful. Left alone, those seeds might have remained just that, and the cosmos would be a vast, dark, and nearly empty expanse. Enter the silent architect. Dark matter, immune to the push and shriek of that early radiation, felt only gravity. Those tiny overdensities were like subtle dips in an invisible landscape. Dark matter began to pool there first, slowly, steadily, building up gravitational wells in the darkness. These growing halos of unseen mass became the universe's foundational skeleton. Only later, as the cosmos expanded and cooled, could the ordinary matter finally fall into those pre-built gravitational pits. Think of it like casting a statue. The dark matter forms the intricate wireframe, the armature. The ordinary gas and dust are the molten bronze, flowing into the mold only after the scaffolding is perfectly in place. Without that invisible framework, the material would just puddle and spread, never holding the majestic shape of a galaxy. This process is not just a theory, we can observe its echoes in the grand architecture of the cosmos today. Galaxies are not scattered randomly. They are woven into a vast cosmic web, immense filaments and walls of galaxies stretching across billions of light years, with enormous voids in between. This magnificent structure is a perfect cast of the dark matter distribution that formed first. The luminous galaxies we see are simply where the ordinary matter, the stars, lit up within the densest knots of that ancient, invisible web. To witness this story unfold, cosmologists run the universe in a box. They create supercomputer simulations like the famous Millennium Run, starting with those primordial ripples and the laws of physics. When they include only ordinary matter, the result is a disappointing, faint smear. But when they add the gravitational influence of dark matter, something miraculous happens. The simulation unfolds over billions of years of virtual time. We watch as the dark matter weaves itself into a delicate, filamentary lattice. Then, like dew condensing on a spiderweb, the normal matter follows the dark matter's lead, flowing along the filaments and pooling at the intersections. What emerges is a universe that looks uncannily like our own, with clusters, walls, and voids that match telescope surveys with stunning accuracy. One researcher described it plainly: dark matter is the universe's architect. It designed the blueprints and built the load-bearing walls. We and every star we see are merely the interior decoration. This role makes dark matter utterly indispensable. It is not a passive component, it is the active sculptor. Our very existence here in this galaxy, on this planet, is a direct consequence of that invisible scaffolding gathering the raw materials of creation. It forces a humbling perspective. The Milky Way, with its hundreds of billions of stars, is not just floating in emptiness. It is resting at the heart of an immense, spherical halo of dark matter, hundreds of times more massive than all its visible stars combined. We are living deep inside a ghost, and our entire cosmic neighborhood is shaped by its silent, persistent pull. The most detailed maps of dark matter are not drawn by telescopes, but by supercomputers. To see the invisible, scientists build entire universes from scratch. They start with the primordial seeds from the cosmic microwave background, the faint ripples of the infant cosmos. Then they set the rules, programming in the fundamental laws of physics, including the gravitational pull of an unseen component. With a press of a button, they set time in motion, watching billions of years of cosmic evolution unfold in mere months. What emerges is a revelation. Dark matter does not form a uniform haze. It weaves itself into an immense, delicate lattice, a cosmic web of dark filaments stretching across the void, connecting at dense nodes where galaxy clusters will eventually shine. This is the universe's true skeleton, and we can only see it in simulation. Projects like Illustris TNG and the Millennium Run are not video games, they are fundamental research tools. They act as digital laboratories where theories can be tested in ways impossible in the real world. Scientists can adjust the properties of dark matter, for instance, making it cold and slow-moving, or slightly warmer and faster. They run the simulation again and compare the resulting virtual universe to the one we observe through our telescopes. Does the simulated web match the distribution of real galaxies? Do the virtual galaxy clusters have the right mass and shape? The answer has been decisive. A model with cold dark matter, where particles move sluggishly, produces a cosmic web and galaxy population that is a near-perfect match for reality. This computational approach solves a key problem. We cannot put dark matter in a jar, but we can put it in a simulated box a billion light-years across and watch what it does. As one astrophysicist put it, simulations are our laboratories for the cosmos. They allow us to rewind and fast-forward time, to isolate variables and witness the direct consequences of the dark universe's rules. The visualizations from these simulations are not just pretty pictures, they are predictive maps. By showing where the densest knots and filaments of dark matter lie, they tell observational astronomers exactly where to point their most sensitive instruments. They guide the search for the subtle gravitational lensing distortions that will confirm the web's structure. This creates a powerful feedback loop between the digital and the real. A discrepancy between simulation and observation is not a failure, it is a clue. It might point to a new property of dark matter or reveal an overlooked force at play in galactic evolution. Every time we peer deeper into the actual sky and find a structure that matches the simulated one, it is a quiet validation that we are on the right track, that our digital ghost is a true reflection of the invisible reality holding everything together. The digital universe of our simulations found its most dramatic validation in a real cosmic collision. Two massive galaxy clusters, each containing hundreds of galaxies, slammed into one another at millions of miles per hour. This event, catalogued as 1508-5585 but known to all as the Bullet Cluster, provided what many call the smoking gun for dark matter. To understand why, we need to watch the crash in slow motion using different eyes. First, the Chandra X-ray Observatory looked at the scene. It saw the hot gas that fills the space between the galaxies, normal matter heated to millions of degrees. In the collision, this gas behaved like two clouds of smoke. It slammed together, slowed down, and piled up in the center, glowing brightly in X-rays. This is what we expect from stuff that interacts, that feels friction and pressure. Then, astronomers mapped the true mass using gravitational lensing. By measuring how the cluster distorted the light of galaxies far behind it, they could trace where the gravity was strongest, where most of the mass actually ended up. The result was astonishing. The maps revealed two distinct clouds of mass that had sailed clean through the collision site. They were now on either side, separated from the glowing pile of gas in the middle. It was a clean, cosmic separation. The stuff that makes light and heat had gotten stuck. The stuff that provides most of the gravity had passed through like a phantom. This observation ruled out entire categories of explanation. If the mystery were just a modification of gravity, the gravity would be centered on the visible gas. It was not. If dark matter interacted with itself like normal matter, it would have also slowed down and pooled in the center. It did not. The Bullet Cluster showed with breathtaking clarity that dark matter is a distinct substance. It feels gravity, allowing it to clump and shape the cosmos, but it does not feel the electromagnetic force that makes normal matter crash, slow, and glow. One leading researcher on the project described it this way: "It is as close to a direct detection as we can get without seeing the particle itself. We are watching its shadow move independently across the sky." The composite image tells the whole story. The pink clouds of hot gas from Chandra are nestled in the center, bruised from the impact. The blue contours from the lensing map, representing the bulk of the mass, flank them on either side, ghosts that have already moved on. This single snapshot captures the essence of the dark matter mystery. It is real, it is massive, and it is profoundly aloof, a cosmic entity that builds the stage but refuses to step into the spotlight. This evidence steers us toward an even more intriguing question. If dark matter truly is this collisionless ghost, what happens when we look for it not in serene halos, but in the most violent crucibles the universe can create? Our galaxy is not an island floating in emptiness. It rests at the heart of a ghost. Every galaxy we see, from majestic spirals to faint dwarfs, is cradled inside an immense, roughly spherical cocoon of dark matter, a halo that stretches hundreds of thousands of light years beyond the last visible star. This is the hidden architecture that explains everything. The flat rotation curves Vera Rubin measured, the gravitational lensing we observe, they all point to this same conclusion. The stars we admire are merely the luminous tip of a vast, invisible iceberg. The halo itself is not a smooth, featureless cloud. According to the Supercomputer Simulations, it should be teeming with substructure. Smaller clumps and streams of dark matter, the remnants of smaller galaxies consumed long ago, orbit within the larger halo like cosmic debris. We may have already seen their fingerprints. Around our own Milky Way, astronomers have found stellar streams, long ribbons of stars that were once part of small satellite galaxies, now stretched out by our galaxy's immense gravity. These streams are like dye tracers in a river, their paths shaped by the unseen contours of the dark matter halo they move through. To map this ghostly cocoon, scientists turn to cosmic tracers. They meticulously track the motions of globular clusters, those ancient balls of stars that orbit the galactic center, and the handful of small satellite galaxies that dance around the Milky Way. A mission like the Gaia spacecraft is revolutionizing this work by precisely measuring the positions and velocities of over 1 billion stars. Gaia allows astronomers to perform a kind of cosmic forensics. By watching how these objects move, they can work backwards to calculate the gravitational field holding them, revealing the shape, size, and total mass of the invisible halo that dictates every orbit. The scale is almost incomprehensible. The visible disk of the Milky Way, with its 100 billion stars, spans about 100,000 light-years. Our dark matter halo extends at least 10 times farther, 1 million light-years across, and contains perhaps 30 times more mass than all the stars, gas, and dust combined. This immense, gentle grip is what stabilizes the entire galactic disk. Without this anchoring cocoon, the rapid spin of the outer stars would have flung the galaxy apart eons ago. As one astronomer simply put it, the galaxy we see is just the glitter on the surface of something much larger and darker. This concept transforms our understanding of home. Our solar system does not merely orbit a center of stars. It travels through an ocean of unseen matter, embedded within this vast, dynamic halo that prompts a fascinating and somewhat personal question. As we move through this invisible sea, does it leave any trace at all on our local celestial neighborhood? The hunt for a ghost requires absolute silence. Far beneath the surface of our world, in places where the very rock above acts as a cosmic shield, humanity has built its most sensitive ears. Laboratories like SNOLAB in an active nickel mine 2 kilometers below Canada, or the Gran Sasso facility under the Italian Apennine Mountains, exist in a realm of profound stillness. Here, the constant rain of cosmic rays and other background radiation from the surface is reduced to a faint whisper. This is the only environment quiet enough to possibly hear the universe's most elusive particle. Scientists are listening for a bump so gentle it would be like detecting a single grain of sand dropped onto a football field from space. The core technology of this search is both simple in concept and breathtakingly complex in execution. Take the LUX-ZEPLIN experiment, a direct successor to pioneering detectors like LUX and ZEPLIN. Its heart is a cylindrical tank containing 10 tons of liquid xenon, cooled to -100 degrees Celsius. Xenon is chosen for its purity and density, a vast, ultra-clear pool of atomic nuclei. The idea is this: if a WIMP, a weakly interacting massive particle, from the Milky Way's dark matter halo happens to pass through, there is a vanishingly small chance it will collide with the nucleus of a xenon atom. That tiny transfer of energy would produce 2 signals: a prompt flash of scintillation light and a delayed pulse of electrical charge as electrons are knocked free. An array of ultra-sensitive photomultiplier tubes lining the top and bottom of the tank waits to capture these twin signatures. The timing and pattern of these signals are the fingerprint researchers use to distinguish a potential dark matter interaction from anything else. Eliminating that anything else is the monumental challenge. Every material used in the detector's construction must be screened for even trace natural radioactivity. The xenon itself is continuously purified. The entire apparatus is often suspended within a larger tank of ultra-pure water, acting as a further shield. Researchers speak of their work as an exercise in extreme cleanliness, scrubbing their experiment of every conceivable contaminant. As one physicist involved put it, we are looking for a needle in a million haystacks, and our first job is to remove every other piece of metal that could possibly look like a needle. This is not the work of a single team, but a global collaboration of hundreds of scientists and engineers, pooling intellect and resources across continents. The act of building and operating these detectors is a triumph of human ingenuity and patience, a decades-long investment in a single, quiet question. To stand in one of these cavernous, clean rooms is to witness a temple to curiosity, where technology is pushed to its limits in the hope of catching a whisper from the dark. A successful detection here would not just identify a particle, it would open a window into the hidden 95% of the universe, forever changing our place within it. While underground labs listen in profound silence, other eyes are turned upward, scanning the heavens for a different kind of signal. The search moves from the quiet of a shielded cavern to the vibrant, energetic canvas of space itself. Orbiting high above Earth's obscuring atmosphere, observatories like the Fermi Gamma Ray Space Telescope act as cosmic detectives, hunting not for the dark matter particle directly, but for the forensic evidence it might leave behind. The theory is elegant. If dark matter particles are their own antimatter counterparts, then when two of them collide, they could annihilate one another in a flash of energy. Alternatively, if certain types of dark matter particles are unstable over cosmic timescales, they could slowly decay. Both processes would produce a cascade of secondary particles, including gamma rays, the most energetic form of light in the universe. Scientists are meticulously mapping the gamma ray sky, searching for an unexplained glow, an excess of these high-energy photons that cannot be attributed to any known celestial object like a pulsar or a black hole. They focus their gaze on places where the invisible stuff should be most densely packed. The heart of our own Milky Way is a prime target, a region where models predict a thick concentration of dark matter. And indeed, Fermi data has revealed a puzzling, diffuse excess of gamma rays emanating from the galactic center. It is a tantalizing hint, a shimmer that matches some predictions of dark matter annihilation. Yet the interpretation is fraught with challenge. The galactic center is also a crowded, tumultuous place, bustling with pulsars, stellar remnants, and complex gas clouds that could also produce similar signals. Distinguishing a dark matter signal from this astrophysical background is like trying to hear a single instrument in a roaring symphony. This is why astronomers also look to quieter cosmic neighborhoods. Dwarf spheroidal galaxies, small, faint satellites of the Milky Way, are considered pristine dark matter laboratories. They contain very few stars and almost no gas, meaning they have very little of the normal astrophysical clutter that could mimic a signal. They are believed to be held together almost entirely by dark matter. By combining observations of many of these faint dwarfs, scientists can stack the data, amplifying any potential whisper of annihilation coming from their dark hearts. So far, no definitive signal has emerged, but each null result helps theorists refine their models, telling them what dark matter is not. The upcoming Nancy Grace Roman Space Telescope will take this indirect hunt to a new level. With a field of view 100 times larger than Hubble's, it will conduct vast surveys of the sky, discovering thousands of new dwarf galaxies and mapping the cosmic web structure with unprecedented precision. This will provide a richer, more detailed map of dark matter's distribution, offering new places to look for those elusive energy signatures. As one astrophysicist working with these space-based observatories notes, we are piecing together a puzzle across the entire electromagnetic spectrum. Every wavelength of light, from radio waves to gamma rays, offers a different clue. The quiet non-detection in one band, combined with a curious excess in another, slowly constrains the possibilities. This expansive, indirect approach reminds us that the answer may not come from a single, dramatic event in a tank deep underground. It might instead emerge as a pattern, a statistical anomaly in the light of distant galaxies, a ghostly fingerprint finally recognized in the deep archival data of a telescope that has been staring at the dark for years. It turns the entire cosmos into our laboratory. With every galaxy and gamma ray burst a potential clue in the greatest detective story science has ever known. Deep underground, another kind of collision is underway. At the border of Switzerland and France, a circular tunnel 27 kilometers long houses the most powerful microscope ever built. The Large Hadron Collider does not look for dark matter by listening for whispers. It attempts to create it from pure energy, by accelerating protons to within a hair's breadth of light speed and smashing them together. It recreates for a fleeting instant the unimaginable conditions that existed a fraction of a second after the Big Bang. In that microscopic fireball, energy condenses into a shower of exotic particles, some of which may have not existed naturally since the universe's first moments. Among them, physicists hope could be the very constituents of dark matter. The challenge is that these particles, by their very nature, would not register in the detectors. They would sail right through the massive apparatus as if it were not there. So how do you find something designed to be invisible? You look for its absence. This is the hunt for missing energy. In every proton collision, the total energy and momentum must be conserved. It is a fundamental bookkeeping rule of the universe. Sophisticated experiments like ATLAS and CMS, each as tall as a 5-story building, surround the collision points. They act as ultra-high-speed forensic cameras, capturing the trajectories and energies of thousands of charged particles produced in the blast. Physicists then add up all the energy they can measure, projecting it onto a plane perpendicular to the beam. If a significant amount of energy and momentum seems to vanish into thin air, recoiling away without any visible particle to carry it, that missing transverse energy could be the signature of a dark matter particle fleeing the scene. Think of it like a game of pool played in total darkness. You hear the crack of the cue ball striking the arrangement, and you can track the sound of several balls rolling and colliding with the bumpers. But if you carefully add up all the momentum from the sounds you hear and find the cue ball has recoiled much more sharply than the visible balls account for, you are forced to conclude something unseen was struck and carried that missing energy away. That is the essence of the search at the LHC. The hope is deeply connected to theories like supersymmetry. If dark matter is the lightest superpartner particle, then the violent collisions might produce heavier, unstable partner particles that would rapidly decay, with one of the end products being this stable, invisible dark matter candidate. The data from billions of collisions is sifted by algorithms, searching for those rare events where the energy ledger does not quite balance. A researcher on the CMS experiment framed it this way: we are probing the highest energies humanity can muster to find the particles with the lowest possible interactions. It is an inverse search, building the most complex machines to find evidence of something by what it does not do. While a direct detection in an underground lab would tell us dark matter is here and now, a creation at the LHC would allow us to study its properties in a controlled way, measuring how it interacts with other particles in that primordial fire. This bridges a profound gap connecting the colossal scales of galaxy formation with the infinitesimal realm of quantum physics. It suggests the same rules that govern the birth of the universe in the first moments also dictate the architecture of the cosmos 13 billion years later. Our most powerful simulations paint a universe of dark matter with sharp, defined edges. But when we compare those digital predictions to the real, observed cosmos, we find the maps do not quite match. The most telling discrepancies lie not in the vast cosmic web, but in the intimate details of individual galaxies. Take the very center of a spiral galaxy like our own. According to the standard cold dark matter model, gravity should have drawn an immense density of dark matter into a sharp peak, a steep cusp right at the galactic core. Yet observations of how stars and gas move in the hearts of many galaxies tell a different story. They suggest a much gentler slope, a smoothed-out core rather than a dense spike. This is the Core-Cusp problem, a quiet but persistent mismatch between what our best theories predict and what we actually see. It is as if the invisible scaffolding has been subtly reshaped from within. One possible explanation points not to dark matter itself, but to the violent astrophysics of the visible universe. When massive stars are born, they live fast and die young, exploding as supernova. These titanic blasts can drive powerful winds, pushing the ordinary gas around and through gravity, potentially sloshing the dark matter around with it, smoothing out that central cusp over billions of years. This process, called stellar feedback, is a reminder that the dark universe and the light universe are in a constant, subtle dance. But another, more radical idea is that dark matter might not be completely collisionless after all. What if dark matter particles can interact with each other through some force besides gravity? In a self-interacting dark matter model, these particles would scatter off one another like billiard balls in the dark. This scattering would transfer energy from the inner, faster-moving regions to the outer halo, naturally eroding the dense central cusp and creating the smoother cores we observe. It is a compelling tweak that solves one puzzle, but it must also pass every other test from the bullet cluster to the cosmic microwave background. A second, equally puzzling mismatch orbits our own galaxy. Our sophisticated simulations of cosmic structure formation predict that thousands of small, dark matter clumps or subhalos should be swarming around a galaxy the size of the Milky Way. These are the leftover building blocks from the hierarchical assembly of the cosmos. Yet when we look up, we see only a few dozen faint dwarf galaxies, not the expected multitude. This is the missing satellites problem. Where are all those dark matter halos? The answer may lie in the delicate process of lighting up the dark. Perhaps the vast majority of those small dark matter clumps never gathered enough ordinary gas to form stars, or the fierce ultraviolet radiation from the first galaxies stripped that gas away before stars could ignite. They would be dark galaxies in the truest sense, invisible halos of pure dark matter drifting silently through our galactic neighborhood. New, ultra-sensitive surveys are now scanning the sky for the faintest stellar glimmers or subtle gravitational effects that might reveal these hidden halos. Each one found helps calibrate our understanding of how galaxies, both bright and dark, come to be. As one theorist working on these distribution puzzles noted, the devil is in the details. The broad strokes of dark matter are settled, but these finer discrepancies are where the next revolution in understanding may occur. They are not failures of the theory, but vital clues. They force us to ask deeper questions about the nature of the dark particle itself and its relationship to the luminous world. Is it truly inert, or does it have a hidden complexity? Does star formation play a larger role in sculpting the dark landscape than we thought? Every graph plotting a predicted density curve against an observed one, every discussion of feedback models versus self-interaction, represents a frontier of inquiry. These mysteries remind us that the story of dark matter is not a finished book, but a manuscript still being written. Its most intriguing chapters hinted at by the subtle tensions between our brilliant simulations and the enduring, complex reality of the night sky. The long-term fate of the cosmos hinges on a silent tug of war. On one side is the relentless push of dark energy, driving the universe to expand at an accelerating rate. On the other is the steady, patient pull of gravity, embodied by the combined mass of everything with dark matter as its heavyweight champion. While dark energy currently dominates the cosmic ledger, dictating our accelerating future, dark matter's role was and remains foundational in shaping what that future will look like. Its gravity acts as the universe's brake pedal, a counterweight that for billions of years slowed the expansion, buying time for galaxies, stars, and planets to form. Without that immense gravitational anchor woven through the cosmic web, the primordial universe would have expanded too rapidly for any structure to ever coalesce. We owe our very existence to that early era of gravitational resistance. Today, that same glue determines what stays together even as the fabric of space itself stretches. While individual galaxies will be pulled ever farther apart over astronomical timescales, The clusters and groups they belong to are held in a lasting embrace by their shared dark matter halos. The Virgo cluster, for instance, with its thousands of galaxies, is not just a temporary gathering. It is a family bound for eternity by an invisible gravitational hand, a permanent island in an ever-widening sea of emptiness. Cosmologists project timelines stretching trillions of years into the future. They run simulations that show stars eventually burning out, galaxies fading from view, and black holes slowly evaporating. What remains long after the last light winks out? The dark matter scaffolding. The ghostly halos and filaments of the cosmic web will persist, a permanent skeleton of a universe that once blazed with light. These dark structures will continue to trace the grand architecture that once hosted galaxies, a silent monument to a more vibrant cosmic age. One astrophysicist described it as the universe's lasting signature, a fossil of gravity written in invisible ink. This perspective connects our search for dark matter to the ultimate narrative of everything. It is not just about what holds galaxies together now, but about understanding the stage upon which the entire cosmic story unfolds from the first second to the last. Contemplating these dark skeletons invites a profound reflection. Our vibrant world of light and life exists within a framework of profound darkness, a framework that will outlast every star. In seeking to understand this hidden mass, we are not just solving a physics puzzle. We are reading the first and final chapters of the universe's story, discovering the invisible threads that weave the past to the most distant future. This cosmic skeleton, invisible and enduring, confronts us with a humbling truth. For all our technological marvels, from the deepest underground labs to the most powerful space telescopes, we remain fundamentally blind to the majority of reality. Our primary sense, sight, and its technological extensions across the electromagnetic spectrum reveal less than 5% of the cosmos. The rest is a silent, dark ocean we can only infer by the ripples it makes in the visible world. This is not a failure of science, but its greatest triumph. It demonstrates our ability to move beyond the limits of our senses, to use reason and mathematics as a new kind of vision. We are like someone in a pitch-black room, unable to see the furniture, but who can map the entire layout by listening to the echoes of their own voice. Dark matter is the echo we have learned to hear. It forces a philosophical shift as profound as the one Copernicus initiated. He showed us we are not the physical center of the universe. Dark matter reveals we are not even at the center of perception, that the reality we experience directly is a minor component of a much vaster, hidden whole. As one philosopher of science noted, we are blind to the majority of matter, yet we know it is there. This statement captures the beautiful paradox of modern cosmology. Our knowledge has expanded precisely by admitting and quantifying our ignorance. It invites a simple but powerful thought experiment. Imagine a species that evolved in a world of pure sound with no concept of light. They develop a sophisticated science of acoustics, mapping their world through echoes and vibrations. Then, one day, they stumble upon evidence of light. They cannot see it, but they can feel its warmth on their skin and observe its effects on materials. They would have to invent a whole new physics to describe this invisible, pervasive force that interacts with their world in subtle ways. In many ways, we are that species, just beginning to feel the warmth of the dark universe. This journey into the unseen reshapes our understanding of what it means to know something. Knowledge is no longer just about direct observation. It is about constructing a coherent story that explains all the clues, from the spin of galaxies to the bending of light, even when the main character remains offstage. Each null result from a detector, each puzzling galactic core, each new simulation is a line in that story. The cultural impact of such a mystery is profound. It weaves itself into our art, our stories, and our collective imagination, becoming a modern myth for a scientific age. The same profound mystery that occupies physicists also fuels the stories we tell. Long before it was a scientific certainty, the concept of an invisible substance shaping reality was a powerful narrative device. In countless science fiction novels, blockbuster films, and television series, dark matter has been reimagined as a cosmic wonder material. It powers faster than light engines in starships, serves as an unstoppable superweapon, or becomes a volatile substance that threatens entire planets. These stories, from the warp cores of Star Trek to the adventures in Doctor Who, tap directly into our collective awe for the unknown. They reflect a deep human desire to give form to the formless, to turn the universe's greatest secret into a tangible element of adventure. While these creative liberties are a far cry from the scientific reality of a collisionless, weakly interacting particle, they serve a vital purpose. They plant a seed of cosmic curiosity in the public mind. A child watching a spaceship jump to hyperspace powered by dark energy credits might one day grow up to ask the real questions that drive astrophysics forward. This cultural fascination is a double-edged sword, however. The very popularity of these ideas can spread misconceptions, leading some to believe dark matter is a glowing, explosive fuel rather than an invisible gravitational scaffold. Scientists themselves have a nuanced view of this phenomenon. Many express appreciation for the engagement and wonder these stories generate. As one cosmologist noted, the best science fiction makes the audience feel the scale and mystery of the cosmos, and that emotional connection is invaluable. It brings people to the doorway of real science, but they also offer a gentle caution. The danger lies in the details, where exciting fiction can harden into mistaken public belief. The real dark matter will not be found in a glowing containment chamber or harnessed as a power source. Its discovery will likely be a subtle signal in a graph, a statistical anomaly in telescope data, a quiet triumph of patience over spectacle. This cultural lens reveals something beautiful about our relationship with the universe. Dark matter has become a modern myth, a blank canvas upon which we project our hopes and fears about the frontiers of knowledge. It bridges the rigorous world of empirical science and the timeless human tradition of storytelling. This interplay encourages us as an audience to do two things at once. We can wholeheartedly enjoy the thrilling tales spun from cosmic mystery, while also learning to separate the poetry of fiction from the precise, often quieter, language of fact. That public wonder stoked by these very stories is not trivial. It translates into something concrete, the sustained interest and support that allows for the decades-long projects, the deep underground laboratories, and the ambitious space telescopes. Every viewer captivated by a fictional universe is a potential supporter of our quest to understand the real one. The search for an invisible universe has sharpened our vision in surprising ways. The extreme technologies built to catch a ghost have quietly transformed our own world, spinning off innovations that touch medicine, security, and the very fabric of our digital lives. This is the hidden dividend of curiosity, where the tools forged to answer a cosmic question find purpose in the human scale. To shield a dark matter detector from natural radioactivity, scientists had to pioneer materials of unprecedented purity and develop shielding methods of immense sophistication. Those same techniques now protect workers in nuclear facilities and help monitor environmental radiation with exquisite precision, creating safer spaces for everyone. The ultra-sensitive photodetectors that listen for a single photon in a vat of liquid xenon are cousins to the sensors that improve medical imaging. The algorithms that sift through billions of particle collisions at the Large Hadron Collider, searching for that one anomalous event, have evolved into powerful data processing tools used in fields from genomics to financial modeling. Even the cryogenic systems that cool detectors to near absolute zero have advanced our mastery of ultra-low temperature engineering, with applications in quantum computing and superconductivity. Experts in the field often note that pursuing the unknown yields unexpected practical rewards. The ripple effect is real. Consider the positron emission tomography scan, a vital tool in modern hospitals for imaging cancer and brain function. Its development was deeply informed by particle physics and the study of antimatter, a close cousin to the dark matter quest. The relentless drive to see the invisible has given us better ways to see inside ourselves. On a grander scale, the monumental international collaborations behind projects like the Large Hadron Collider or the James Webb Space Telescope are feats of human coordination. They create thousands of high-tech jobs, push materials science and computing to their limits, and forge global partnerships that transcend borders, proving that a shared question can be a powerful unifying force. This practical angle underscores a profound truth about fundamental research. We never know which thread of curiosity will weave into the tapestry of daily life. The next generation of dark matter experiments, with their even more sensitive sensors and advanced quantum technologies, may well seed the innovations of tomorrow, from unbreakable encryption to new forms of medical diagnosis. The hunt for the cosmos's missing piece is in itself building a better world. The line between established fact and compelling theory can sometimes blur in the public mind. Dark matter is not a fact in the same way gravity is a fact. We can drop an apple and witness it directly. Instead, it is a hypothesis, but one with such overwhelming and consistent indirect evidence that it forms the bedrock of modern cosmology. Think of it like a criminal investigation where the suspect has never been seen, but their fingerprints are at every scene, their shadow is caught on every security camera, and their actions explain a series of otherwise impossible events. The case is compelling, but the direct apprehension is still ahead. This distinction is crucial, not a weakness of the idea, but a strength of the scientific process itself. Science does not deal in absolute proofs, but in the best explanation that fits all the data. And for the rotation of galaxies, the bending of light, the formation of cosmic structure, and the pattern of the universe's first light, dark matter is that explanation. A common dismissal is that dark matter is merely a placeholder for our ignorance, a fudge factor invented because our equations do not work. This misunderstands how science progresses. A placeholder is an empty variable, a question mark. Dark matter is a detailed framework with immense predictive power. It successfully predicted the exact pattern of hot and cold spots we would find in the cosmic microwave background years before we measured it with precision. It predicted the separation of mass from visible gas in colliding galaxy clusters like the Bullet Cluster. When you input dark matter into supercomputer simulations, you get out a universe that looks astonishingly like our own. That is not a placeholder, it is a powerful engine of discovery. Some sensational headlines or fringe theories suggest dark matter could be dangerous, a mysterious substance that might swallow stars or unravel planets. This conflates dark matter with speculative ideas like primordial black holes or exotic, unstable particles. The dark matter that forms the cosmic web, according to all evidence, is incredibly benign. It interacts so weakly that trillions of these particles are passing through your body every second without a single collision or effect. It poses no more threat than a beam of moonlight. In fact, without its gentle, pervasive gravity, our galaxy would not exist, and neither would we. Another myth is that dark matter somehow disproves Einstein's theory of general relativity. The opposite is true. Dark matter is a solution within Einstein's framework, not a rejection of it. General relativity tells us that mass and energy curve spacetime, creating gravity. Dark matter is simply a form of mass we had not accounted for. It is the missing source term in Einstein's magnificent equations, the invisible mass that explains why spacetime is curved in the ways we observe. Finding dark matter would be a triumph for relativity, not its downfall. Scientists themselves are the first to clarify these points, As astrophysicist Priyamvada Natarajan has stated, calling it dark matter is a constant reminder of our ignorance about its nature, but not about its existence. The evidence is there. The goal of scientific literacy is to understand the weight of that evidence, to distinguish between a wild guess and a well-supported model that makes testable predictions. This clarity empowers us. It allows us to navigate sensational headlines, to appreciate the real wonder without the fictional fear, and to understand that the ongoing hunt is a sign of science working as it should, methodically closing in on a profound truth. With these myths cleared away, the path forward comes into sharper focus. The next generation of experiments is already taking shape, moving from blueprints to concrete reality. In laboratories deep underground, the successor to current xenon detectors is being planned. Named Darwin, this observatory aims to be the ultimate liquid xenon time projection chamber, a vessel containing potentially 50 tons of ultra-pure xenon. Its scale is staggering, a swimming pool-sized volume of liquid waiting for a ghostly touch. The goal is not just to be bigger, but exponentially quieter, pushing sensitivity to a realm where even the faintest whispers of a WIMP interaction could rise above the final, irreducible background of natural radioactivity. As one physicist on the project frames it, Darwin is about crossing a threshold. We are moving from placing limits on what dark matter is not, to entering a territory where we must see something. It is a direct, high-stakes hunt for the particle itself, with construction expected to begin before the end of this decade. While Darwin listens in the deep quiet, a new eye will open on a mountaintop in Chile. The Vera Rubin Observatory, with its 8.4-meter mirror and a camera the size of a small car, will begin the legacy survey of space and time. For 10 years, it will scan the entire southern sky every few nights, creating an unprecedented motion picture of the cosmos. It will catalog billions of galaxies and measure the subtle distortions in their shapes caused by gravitational lensing. This will produce the most detailed map yet of the cosmic web's dark matter distribution, revealing its filamentary structure with breathtaking clarity and potentially uncovering thousands of those elusive, pure dark matter halos orbiting our galaxy. The project's lead scientist has said the survey will transform our view of the dark universe from a sketch to a high-definition image, pinpointing exactly where to focus our most powerful telescopes. Above the atmosphere, the European Space Agency's Euclid mission is already on its journey. This space telescope is designed to measure the geometry of the dark universe with exquisite precision. By observing billions of galaxies out to vast distances, Euclid will chart how the cosmic web has evolved over 10 billion years. This will tightly constrain the properties of both dark matter and dark energy, testing whether dark matter truly is cold and collisionless or if it possesses a subtle warmth or capacity for interaction. The mission's data will work in concert with Rubin's, providing a stereoscopic view of the universe's hidden skeleton. A senior scientist on Euclid describes it as a cosmic cartography mission. We are not just taking a snapshot, we are creating a three-dimensional atlas of the invisible, showing how gravity painted the universe over cosmic time. Parallel to these colossal experiments, theoretical minds are exploring frontiers just as daring. What if dark matter is not a neutral particle but carries a kind of hidden charge, leading to asymmetric dark matter models where particles and antiparticles behave differently? Others are forging deeper links with the ghostly neutrino, suggesting dark matter could be part of a larger, hidden family of particles that only communicate with our world through portals we have yet to find. The mood in the field is one of cautious optimism. Many researchers believe the combination of these new observational tools and theoretical creativity makes a breakthrough within the next 2 or 3 decades not just possible, but likely. The director of a major astrophysical institute recently noted, "We have surrounded the mystery from every angle. it is a matter of time before one of these avenues yields the crucial clue. This forward momentum highlights a beautiful truth about science. The story of dark matter is not a static puzzle waiting to be solved. It is a living, breathing quest that evolves with every null result and every new map of the sky. The tools we build today were unimaginable to the pioneers who first charted galaxy rotation, and the questions we ask now will shape the experiments of tomorrow. This dynamic chase invites all of us to stay engaged, to watch as the data from Rubin and Euclid floods in, to follow the construction of Darwin. We are not distant observers of a finished story, but witnesses to a chapter being written in real time. The anticipation itself is a kind of discovery, a shared human experience rooted in wonder, and it leads to one final, profound consideration. If and when that signal is finally confirmed, when the ghost steps into the light, what would such a discovery truly mean for us? The possibility lingers in every silent detector and every unexplained data set. What if, after decades of searching, dark matter remains forever hidden from our grasp? This is not a failure of science, but a scenario that would force a profound and thrilling reimagining of reality itself. The search would not stop, it would pivot. Attention would turn with renewed vigor to the most compelling alternatives, ideas that have been waiting in the wings. Foremost among them is modified Newtonian dynamics, or MAN. This theory proposes that our understanding of gravity, while perfect for planets and apples, breaks down at the incredibly weak accelerations found in the outer reaches of galaxies. In this view, there is no missing mass. Instead, gravity itself behaves differently on cosmic scales, providing the extra pull needed to explain galaxy rotation without any invisible particles. For a time, this idea could experience a major resurgence. Scientists would re-examine every piece of evidence, from rotation curves to the bullet cluster, through this radically different lens. They would ask if a more sophisticated theory of gravity, perhaps one that connects to the mysterious nature of space-time itself, could finally explain it all. This path would represent a paradigm shift as monumental as the one from Newton to Einstein. It would mean that the force we thought we knew, gravity, holds a deeper secret that only reveals itself in the vast emptiness between stars. As physicist Mordechai Milgrom, the architect of MAN, once reflected, the universe is under no obligation to make sense to our preconceptions. A null result would be a direct challenge to our preconceptions. Yet, even modified gravity faces its own formidable hurdles. Explaining the precise patterns in the cosmic microwave background or the clean separation of mass from gas in colliding clusters without some form of unseen matter is an immense challenge. This could push theorists toward something even more radical, a complete overhaul of physics that unites gravity and quantum mechanics in a new framework, where what we perceive as dark matter is actually a shadow cast by extra dimensions or a quantum effect of the vacuum of space. The philosopher of science Karl Popper noted that good science is defined by its falsifiability, its willingness to be proven wrong. If dark matter eludes detection indefinitely, that very elusiveness becomes a powerful form of data. It forces a correction. A senior researcher on one of the major detector collaborations put it plainly, not finding something is also a discovery. It tells you where not to look and pushes you to think more creatively. This resilience is the engine of scientific progress. Each dead end, each silent experiment narrows the path and refines the question. The pursuit itself, with its monumental telescopes and deep underground labs, expands the boundaries of our technology and our collective imagination. It teaches us how to ask better questions. So while the evidence today strongly points to a universe woven through with invisible matter, being open to a different outcome is a sign of intellectual strength. It means we are truly listening to the cosmos, ready to be surprised. This openness transforms the search from a simple hunt for a particle into a deeper inquiry into the nature of reality, matter, and the fundamental forces that bind the cosmos. Whether the answer is a ghostly particle or a rewritten law of physics, the journey irrevocably changes our place in the universe. Gravity's great cosmic rival is not another force, but an even deeper mystery. We have spent our journey exploring dark matter, the invisible glue that sculpts galaxies and holds them together, yet this glue accounts for only about 27% of the universe. The lion's share, a staggering 68%, is something entirely different and even more enigmatic: dark energy. Together, these two dark components make up 95% of everything, a humbling reminder that the cosmos we perceive is merely the visible frosting on an immense, unknown cake. While dark matter pulls with the familiar force of gravity, gathering matter into structures, dark energy pushes. It is a repulsive pressure inherent to the fabric of space itself, causing the expansion of the universe to accelerate, not slow down. This is the fundamental duality shaping cosmic evolution, the great tension between the clump and the stretch. One cosmologist beautifully described them as the yin and yang of the universe, two opposing influences written into the empty canvas of space. To grasp their difference, think of a simple analogy. Imagine the universe as a vast, rising loaf of raisin bread. Dark matter is the flour that clumps together to form the raisins themselves, the dense structures like galaxies and clusters. Dark energy is the yeast causing the entire dough to expand, pushing the raisins ever farther apart. One builds the islands, the other widens the sea between them. Their properties are mirror opposites in key ways. Dark matter, as we have seen, is clumpy. It gathers under its own gravity to form halos and filaments, the cosmic web. Dark energy, by all current evidence, is perfectly smooth and uniform. It does not clump or cluster. It is a property of empty space that is the same everywhere, a constant background hum of repulsion. Dark matter's influence was dominant in the early universe, its gravity slowing the expansion and allowing time for galaxies to form. But as the universe grew larger and more diffuse, the push of dark energy began to win. Roughly 5 billion years ago, it crossed a threshold, and the expansion of the cosmos started to accelerate, a discovery that earned the Nobel Prize in 2011. This interplay dictates the ultimate fate of everything. The dark matter scaffolding ensures that galaxies and clusters remain bound together for all time, even as the space between these giant structures is stretched by dark energy. Our local group of galaxies, including Andromeda and the Milky Way, will eventually merge into one, held tight by their shared dark matter halo. But every other galaxy cluster beyond our local group will be pushed away by the accelerating expansion, eventually fading from view. Missions like the European Space Agency's Euclid Telescope and the upcoming Nancy Grace Roman Space Telescope are designed to study this cosmic tug-of-war with unprecedented precision. By mapping the three-dimensional distribution of galaxies and measuring how that structure has evolved over 10 billion years, they will measure the precise tug of dark matter's gravity and the relentless push of dark energy's repulsion. Understanding one may very well shed light on the other, as some theorists explore whether they could be two faces of a single, unified phenomenon, perhaps connected to the quantum nature of the vacuum. For now, they remain distinct, the two dominant yet invisible actors on the cosmic stage. Clarifying this distinction is vital, as the names are often confused. Dark matter is the unseen mass, the cosmic glue. Dark energy is the unseen pressure, the cosmic antigravity. One gathers, the other disperses. Together, they compose the vast majority of a reality that remains hidden from our eyes, a dual mystery that defines not only what the universe is made of, but where it is ultimately going. This cosmic budget, 5% familiar atoms, 27% dark matter, and 68% dark energy, is the most important equation we are trying to solve. It tells us that the story of the cosmos is far stranger than we ever dreamed, a narrative written in invisible ink, where the very vacuum of space holds the key to our future. This grand quest for understanding is not confined to university labs or mountaintop observatories. It spills out into classrooms, onto computer screens, and into the public imagination, where the next generation of explorers is already being inspired. Across the globe, educators and scientists are working to make the cosmos accessible, transforming complex ideas into interactive experiences. Planetariums now feature dazzling shows that take audiences on journeys through the cosmic web, visualizing the dark matter halos that hold galaxies together. Projects like GalaxyZoo invite anyone with an internet connection to become a citizen scientist, classifying real images of galaxies captured by telescopes. This collective effort has led to genuine discoveries, with volunteers helping to identify rare objects and patterns that professional astronomers might have missed. As one educator involved with these programs notes, the most powerful tool in science is a curious mind, and we find them everywhere. Organizations like NASA and CERN have developed vast libraries of free, engaging resources. Interactive simulations allow students to manipulate the parameters of dark matter and watch a virtual universe evolve. Social media campaigns break down complex concepts into short, compelling stories, bringing the frontier of cosmology directly to the public feed. The goal is twofold: to spark a lifelong fascination with the universe and to actively diversify the future workforce in science, technology, engineering, and mathematics. By showing that cosmic mysteries belong to everyone, these initiatives break down barriers, inviting people from all backgrounds to see themselves as part of the story. A teacher from an under-resourced school district shared how using these free NASA materials transformed her classroom. "My students were not just learning about gravity, they were mapping it. They felt like they were part of the team at the Space Telescope because in a way they were." The success stories are deeply personal. A high school student in a remote town participating in an online research program helped analyze data from a radio telescope, contributing to a study on galactic rotation. A community college team built a simple cloud chamber to detect cosmic rays, a tangible connection to the particle physics that underpins the dark matter search. These experiences prove that you do not need a PhD to contribute to humanity's grand questions. You just need curiosity and a connection. This section of our journey ends with an open invitation. Links to these citizen science projects and educational resources will be provided in the description below, a direct pathway for you to join the hunt. Unraveling the universe's deepest secrets has always been a collective human endeavor, from ancient stargazers to modern citizen scientists. By fostering this connection, we ensure the journey of discovery does not end with us, but ripples outward, inspiring the minds that will one day solve the mysteries we can only now map in the dark. The immense telescopes and deep underground laboratories represent a monumental investment of human creativity and resources. This naturally invites a profound question, one that ethicists and scientists alike have grappled with for generations. In a world facing immediate challenges, from environmental concerns to social needs, is it right to dedicate billions of dollars and decades of effort to search for something we cannot see? This is not a simple question, and it deserves a thoughtful conversation. Critics of such large-scale fundamental research argue that these resources could be redirected to solve tangible problems here on Earth. They point to pressing needs in healthcare, education, and infrastructure, suggesting that the pursuit of cosmic mysteries is a luxury we cannot afford. This perspective champions a focus on the here and now, ensuring our collective well-being before reaching for the stars. It is a viewpoint rooted in compassion and practical urgency, and it challenges the scientific community to justify its ambitions. Advocates, however, offer a different vision. They argue that the drive to understand the universe is a fundamental part of what makes us human. This curiosity, this need to look beyond the horizon, has historically been a powerful engine for practical innovation. The technologies spun off from particle physics and space exploration, from medical imaging to global communications networks, have repeatedly transformed daily life in unexpected ways. The quest to map dark matter is pushing the boundaries of sensor technology, data analysis, and materials science, seeds that may grow into the solutions for future earthly challenges we cannot yet foresee. Furthermore, they highlight the intangible benefits. Projects like the international collaborations behind the Large Hadron Collider or the James Webb Space Telescope are feats of peaceful global cooperation. Scientists from nations with complex political relationships work side by side, united by a shared question that transcends borders. This model of collaboration, as one ethicist notes, demonstrates that our common curiosity can be a stronger bond than our differences. It fosters a long-term perspective, encouraging societies to invest in generational knowledge and to think in time frames longer than an election cycle. This cosmic perspective also cultivates a profound sense of humility and unity, seeing our world as a fragile, pale blue dot nestled in an invisible web of dark matter can reshape our priorities. It underscores that we share one planetary home, making the care for it and for each other not just an ethical choice, but a necessary one for our continued story. The debate ultimately centers on balance. Responsible science does not exist in a vacuum, separate from societal needs. It requires ongoing dialogue about priorities, transparency in funding, and a commitment to ensuring that the pursuit of knowledge also works to uplift humanity. The most compelling argument may be that we need not choose between Earth and the cosmos. Understanding our place in the universe deepens our responsibility to our planet, while solving earthly problems enables us to continue looking upward. This ethical reflection is not a sidebar to the science, it is woven into its very fabric. It reminds us that every decision to build a telescope or a detector is a human decision, reflecting our values, our hopes, and our vision for the future. It prepares us to consider the ultimate meaning of this quest, not just for physics, but for the human spirit looking up at a star-filled sky, wondering what holds it all together. The cosmos has whispered its secrets in the language of motion and light, and we have learned to listen. From the stubborn flatness of a galaxy's spin to the ghostly separation of mass in a cosmic collision, the evidence for dark matter is not a single clue but a chorus, each line of inquiry singing the same refrain. Most of the universe is built from something we cannot see. This journey has taken us from the foundational work of Vera Rubin, whose meticulous observations first revealed the hidden weight of galaxies, to the global, multi-generational experiments of today, where scientists in deep underground labs and in control rooms of orbiting telescopes collaborate in a shared pursuit of the invisible. We have walked through the compelling candidates from the heavy, elusive WIMP to the wave-like action, and witnessed the technological marvels, the vats of liquid xenon and the gravitational lensing surveys, all engineered to catch a ghost. Through it all, one truth stands clear. Dark matter is the essential cosmic architect. Without its silent, pervasive gravity, galaxies would fly apart, the cosmic web would never have formed, and the stars we use to navigate the night sky would simply not exist. Our very place in the universe is a gift from the dark. This mystery does more than reshape our cosmic maps. It redefines our relationship with reality itself. It teaches us that knowledge often begins not with seeing, but with recognizing the limits of our sight. It connects each of us gazing up from our small world to the vast, invisible architecture that cradles every galaxy. It is a profound reminder that the universe is under no obligation to be obvious, and that our greatest discoveries often lie in learning to ask better questions of the darkness. Let this exploration be an invitation to keep looking up with wonder, to stay curious about the hidden layers of reality, and to share in the collective human project of understanding our spectacular, mysterious home. What questions did this journey spark for you? Share your thoughts below, and if you are eager for more deep dives into the cosmos's greatest secrets, subscribe to continue exploring with us. The story of the universe is still being written, and the next chapter is waiting.